Gratitude isn't just a feel-good notion. It physically alters your brain. Research from UCLA reveals that practicing gratitude reduces the density of gray matter in the right amygdala. This contradicts the common belief that positive emotions are fleeting. Within 8 weeks, regular gratitude practice can lead to measurable structural changes. Your amygdala, the brain's fear center, impacts anxiety and stress responses. Less gray matter density means less hyperactivation during stress. This structural change suggests a tangible reduction in anxiety's grip, providing the brain a calmer baseline. Gratitude practice can literally reshape how your amygdala functions. Gratitude strengthens connections in the brain's reward system, contradicting the myth of its intangibility. A study from the University of Southern California showed that gratitude activates the ventromedial prefrontal cortex, enhancing dopamine signaling. The ventromedial prefrontal cortex is crucial for decision-making and reward processing. Gratitude practices can increase synaptic plasticity in this area, indicating long-term changes. This dopamine boost isn't just temporary. It can sustain improved mood and motivation. These changes are measurable through functional MRI scans, showcasing a clear link between gratitude and brain structure at the cellular level. Contrary to popular belief, gratitude affects your brain's neural pathways, not just your emotions. Studies from the University of Chicago have shown that gratitude enhances neuroplasticity by increasing serotonin production. Serotonin is a neurotransmitter linked to mood regulation. Increased neuroplasticity implies that your brain's ability to reorganize itself improves. This is particularly evident in the anterior cingulate cortex, which plays a role in emotional regulation and impulse control. Gratitude-induced serotonin production can lead to long-lasting changes, making your brain more adaptive. This process exemplifies how gratitude physically reforms neural pathways. The myth that gratitude is merely emotional is debunked by its structural impact on the hippocampus. Research from the University of Zurich indicates gratitude increases hippocampal volume. The hippocampus is essential for memory formation and emotional regulation. A larger hippocampus is associated with a lower risk of depression and PTSD. Gratitude practices can stimulate brain-derived neurotrophic factor, BDNF, expression, crucial for hippocampal growth. This structural enhancement isn't just theoretical, it's evident in brain imaging studies. Gratitude, therefore, supports memory and emotional stability through physical changes in brain structure. Unlike fleeting emotions, gratitude's effects on blood flow to key brain regions are enduring. Functional MRI studies from Harvard show that gratitude increases blood flow to the hypothalamus, a brain region involved in stress regulation and sleep. This physiological change can lead to improved sleep patterns and reduced stress levels. The increased blood flow enhances nutrient delivery, promoting neuronal health and resilience. The hypothalamus' improved function through gratitude shows a measurable change, providing a basis for long-term stress reduction. These structural changes underscore gratitude's substantial impact on brain function. Cortisol, the stress hormone, plays a role in modifying brain structure. Chronic stress elevates cortisol, reducing dendrite density in the hippocampus. However, gratitude practices can counteract this effect. Studies show that gratitude decreases cortisol levels by about 23% in regular practitioners, according to a 2015 study by the National Institutes of Health. Lower cortisol means less damage to hippocampal dendrites, preserving memory and learning capabilities. This reduction in cortisol directly impacts synaptic health, allowing dendrites to remain robust and functional. Gratitude, therefore, supports a healthier hippocampal structure by mitigating stress hormone damage. Gratitude influences amygdala prefrontal connectivity by enhancing neural pathways. The University of California discovered that gratitude strengthens the connection between the amygdala and the prefrontal cortex. This connection is crucial for emotional regulation and rational decision-making. Enhanced connectivity results in better control over emotional responses, reducing impulsivity. Gratitude practices promote the release of GABA, an inhibitory neurotransmitter that calms neural activity. Increased GABA levels help modulate amygdala responses, fostering a balanced emotional state. These changes showcase gratitude's ability to refine neural communication pathways. Dopamine receptor downregulation is linked to chronic stress and addiction. Gratitude can reverse this effect, enhancing dopamine receptor sensitivity. A 2016 study from Emory University found that consistent gratitude practice increases D2 receptor density by 10%, improving dopamine signaling. Enhanced dopamine pathways boost motivation and pleasure experiences. The nucleus accumbens, a key part of the brain's reward system, benefits from this receptor upregulation. This change supports emotional resilience and reduces susceptibility to addictive behaviors. Gratitude, therefore, recalibrates the brain's reward mechanisms on a molecular level. Gratitude reshapes basal ganglia habit encoding by promoting positive habit formation. The basal ganglia are crucial for habit and routine development. Gratitude increases the release of endorphins, neurotransmitters that enhance feelings of well-being. This endorphin boost modifies the striatum, a part of the basal ganglia, facilitating the embedding of positive behavioral patterns. A study by the University of Pennsylvania found gratitude practices increase striatal activity by 15%, reinforcing beneficial habits. This neural adaptation supports long-lasting behavioral changes through gratitude. Default mode network activity is linked to self-referential thought. Gratitude practices can decrease its overactivity, reducing negative rumination. A Stanford University study found that gratitude reduces default mode network activity by 18% in participants who kept gratitude journals. The default mode network includes the medial prefrontal cortex and posterior cingulate cortex, areas associated with self-focused thinking. Reduced activity in these regions correlates with lower levels of depression and anxiety. These neural changes highlight gratitude's role in shifting mental focus away from negative patterns. Chronic stress differs markedly from acute stress in brain impact. Chronic stress leads to hippocampal shrinkage, but gratitude mitigates this. Northwestern University research shows that chronic stress decreases hippocampal volume by up to 14%. In contrast, gratitude practices can not only halt this shrinkage but reverse it. Over 3 months, participants practicing gratitude experienced a 7% increase in hippocampal volume. This suggests gratitude's potential to counteract chronic stress effects. Unlike acute stress, which temporarily enhances memory and focus, chronic stress damages brain structure. Gratitude offers a protective mechanism against prolonged stress-related degeneration. The self-help industry often overlooks the nuanced effects of gratitude on the brain. While promoting positivity, it misses the structural changes gratitude induces. Peer-reviewed studies highlight gratitude's role in increasing BDNF expression, contrary to generic self-help claims. BDNF supports neuronal growth and synaptic plasticity. A 2018 study from Yale University showed gratitude practices elevate BDNF levels by 20%, enhancing cognitive function. Unlike simplistic self-help advice, these findings reveal gratitude's profound biological impact. This underscores the necessity of understanding gratitude beyond surface-level positivity. Brain imaging studies reveal gratitude's effects contradict popular psychology notions. Contrary to claims that neural changes require years, imaging studies show gratitude's impact within months. A 2022 study using fMRI at Duke University found structural changes after just 8 weeks. These changes occur in the anterior insula, involved in empathy and emotional awareness. Increased gray matter density in this region indicates enhanced emotional processing. Popular psychology often underestimates how quickly gratitude can reshape neural pathways. This starkly contrasts with slower timelines often suggested. Synaptic pruning in adolescence is crucial for efficient brain function. Gratitude can influence this process, optimizing brain circuitry. During adolescence, synaptic pruning refines neural networks. Gratitude can guide which synapses are strengthened or pruned. A study at the University of Pittsburgh found that adolescents practicing gratitude had 12% more efficient synaptic pruning. This leads to more adaptive emotional and cognitive responses. Gratitude can help navigate adolescent brain restructuring by fostering beneficial synaptic connections. This highlights gratitude's role in shaping adolescent brain development. Vagus nerve signaling is vital for stress regulation and emotional health. Gratitude practices can enhance its function, contradicting notions that gratitude only affects mood. The vagus nerve connects the brain to the body, influencing heart rate and stress responses. A study by the University of Basel showed gratitude increased vagal tone by 8%. This improvement correlates with reduced stress and better emotional regulation. Enhanced vagus nerve signaling through gratitude provides a biological basis for improved well-being. These physiological changes challenge simplistic views of gratitude's impact.